All right, ladies and gentlemen, your class recording has started. So, at the beginning of this week, we talked about our classification of matter and how we look at all the matter that's out there in the universe and we put it into categories. And we said that the reason why we make categories, right? Well, let's review. We've talked about categorizing things before, things like the periodic table and some other things we talked about. Why do we categorize things? What does that do for us? Organizes it. Okay, good. All right, so it's a little bit easier to find information. There's one other thing maybe that we talked about here. So go ahead.
Puts things with the same properties together.
Puts things with the same properties together. That's an advantage because why?
So it's like easier to distinguish.
So it's easier to distinguish them. Okay. What about if we encounter something that we don't know? Why is the categorization system helpful?
It's easier to see which group it connects more with.
Okay. If we know what group it connects with, right, even though we may not know about that specific material, if we know it's in that group, we can maybe make some assumptions or some educated guesses about that material that we don't know about because it's grouped with these things, right? And so that's, one of the reasons why we come up with these categories. Pure substances are all similar to one another. And so we can make some assumption if we say that, oh, this material that I don't know, because let's say you didn't know what water was, right? Is that, oh, well, it's a pure substance compound. If you knew what other pure substances and other compounds were, you might be able to make an educated guess about what water was like, all right? So that being the case, right, we come up with all these things. But in the process of talking about those categorizations of matter, we talked a little bit about states of matter. And, you're familiar with the big three, solid, liquid, gas. And then we also added a couple on there. Plasma at the high end of the temperature spectrum, right? High energy particles. And then Bose-Einstein condensate down at the lower end. Today, we introduced the kinetic theory of matter. So, based on the fact that we call this the kinetic theory of matter, you should be able to tell me a couple things about it, just because its name is the kinetic theory of matter. So what I want you to do is I want you to talk to the person next to you for 30 seconds and see if you can come up with at least two things that the kinetic theory of matter should tell us or relate to. 30 seconds, go. Okay, so in your 30-second discussion about the kinetic theory of matter, tell me, what did you discuss and why do you think that that relates to our kinetic theory of matter? So Nick, I saw you had your hand up earlier. If you want to start us off, you can go ahead.
It has something to do with the particles moving.
It has something to do with the particles moving. Which part of its name suggests that?
Kinetic.
The kinetic part, right? So it has to do with particles moving, right? What else? What else did you discuss in your groups? You all talked for 30 seconds. So, Connor, go ahead.
How fast the particles are moving in the substance.
Okay, that relates, that's the kinetic part, right? Relating to the motion of those particles, okay? What else? What else did you discuss? Mark, go ahead.
Why it happens?
Why it happens, what part of its name suggests that?
Theory.
The theory part, right? Remember, theories explain things. Why do things happen? So if this is a kinetic theory, we're dealing with motion of the particles to explain something. And that's where we're headed today. So first, a couple of things that the kinetic theory assumes about matter. First, all matter is made up of tiny particles that could be atoms or that could be molecules, depending on what we're talking about, that are in constant motion. All matter is made up of tiny particles, atoms or molecules, depending on whether we're talking about an element or a compound or a mixture for that matter, that are in constant motion. Like we said, that's the kinetic part. The theory part is the explaining part. Second assumption of the kinetic theory. As the temperature of that substance increases, the particles move faster. Something I think a lot of you are probably already familiar with. Third assumption. Even though we may have two substances at the same temperature, that does not necessarily mean their particles move the same. Because the temperature, while it measures how fast, it actually measures kinetic energy. And if you remember from a long way back, kinetic energy actually depends on a couple of things. Ke equals 1/2 mv squared. So it depends on their velocity, their speed, that's the v part, but it also depends on the mass. So even though we may have two substances at the same temperature, that does not necessarily mean their particles move the same speed. Good there? A couple more things. There are two factors that determine the state of matter that a substance exists in. Two factors. One is the movement, or the temperature. I think that's the factor that most of us focus on exclusively, right? You heat something up, it melts. You heat it farther, it boils and turns into a gas. But there are other factors, specifically the forces of attraction between the particles, which is something we have introduced earlier in the year when we talked about properties of materials and stuff like that. Oh. So two factors that determine the state of matter. First, motion of the particles. Second, forces of attraction. Keep those two things in mind as we move forward. And we're going to actually use that a lot over the next couple of days when we talk about what state of matter something exists in, how does it change from one state to another, etc., etc. All right, good there? Okay. First, states of matter, right? Solid, liquid, gas, right? We introduced plasma the other day, and then we also introduced Bose-Einstein condensate. For this discussion, we're going to focus on these three. We're going to focus on the big three, okay? All right. Starting off, there's plasma. Starting off, gases. Back in 5th grade, or 6th grade, or whatever you start learning about states of matter. Okay? Actually, you start learning about states of matter in like 1st grade, but explaining things a little bit more. Okay? What are the two things that we say characterize a gas? What are two properties of something that exists in the gaseous state? Okay, Mark?
No defined shape and no defined volume.
No defined shape, no defined volume, right? That it will fill up whatever container it's in. If we put it in a big room, that gas will spread out as far as it can until it can't go anymore. And it will fill up whatever shape container we put it in. Square, circle, oval, whatever it is. Okay? And that's true. But there are reasons behind why that's happening. And that's where the kinetic theory comes in. So particles of a gas are in constant random motion at very high speeds. And I think that most of us have probably got that information somewhere along the way, possibly a little bit later than 5th grade. But particles of a gas are in constant random motion at very high speeds. But we said that there are two factors that determine the state of matter, right? What are the two factors that determine the state of matter that something exists in? Eris?
Mass and volume.
No, no. What are the two factors that determine the state of matter that something exists in? You just wrote it down. The previous thing that you wrote down before this one. Nick.
Motion of the particle.
Motion of the particles and
Forces of attraction.
forces of attraction. So here, what is it telling you about the motion of the particles?
Very fast.
Very fast. If those particles are moving very, very fast, how much do you think that they attract each other?
Not much.
Not much, right? If they attracted each other strongly, would they be able to move very fast? Probably not. There would be things holding them back. So, right, gases have more energy than liquids or solids of the same material. That's the high speed part. Generally, that energy comes in the form of what? Or how do we give it that energy? How do those particles get more energy? What do we do to something to make it into a gas? Heat it up, pretty much, right? Doesn't necessarily have to be heat, but that's the easiest one, right? In addition to their fast motion, the motion of one particle is not affected by the other particles. The attraction between the particles is so small that pretty much we ignore it. So, motion, attraction. Lots of motion, very little attraction. Those are the two reasons why gases will have no defined shape and no defined volume, right? The individual particles just have nothing to do with one another. They go along their merry way. They can do whatever they want to. Okay? As we go along and talk about these states of matter, there's a good analogy that goes along with these states of matter, and that would be kids in school. Okay? Let's think of more elementary school, because you guys are kind of out of that phase a little bit, right? But what part of the school day might be a good analogy for something in a gaseous state?
When the bell rings at the end of the day.
That could be when the bell rings at the end of the day, because everybody leaves the school and goes their scattered ways, right? That's one example. How about something during the school day? Recess, right? Same idea, right? Volume expands, they fill out as much as they can, right? Everybody's moving in random fashion, right? There is probably, it's not the best, it's not the best analogy, because the particles on recess do have interaction with each other, right? If somebody's playing tag or you're playing football or whatever it is, okay? But lots of space in between the kids, fast motion. One kid is not necessarily affected by another kid, right? There's end of the school day would be good too, right? Everybody spreads out, we're moving faster, we're going our separate ways. That would work too. Okay? Good there? All right. And like I said, right, that constant motion at the high speed explains why a gas can fill its container, even if there's another gas in that space. If there's one class of kids already on recess and another class of kids joins them, does that necessarily change what the first class of kids was doing? Depends on the size of the playground, obviously, but, right, if it's a big enough playground, the first set of kids might not even notice the other set of kids are there. And that's how it is with gases as well. Because those gases move so fast, and there's so much space in between them, and they have so little to do with each other, don't even know the other one's there. All right, good there? Okay, next, liquids. You learned back in 5th grade 2 properties of liquids. What are the 2 properties of liquids that you learned back in 5th grade or earlier?
No definite shape, but definite volume.
No definite shape, but a definite volume, right? So why is that? Particles of a liquid move more slowly than gases and are more closely packed. What does that mean about how much energy these particles have versus the energy of gas particles? Mark, good.
Not quite as much.
Not quite as much, right? Don't move as fast, not as much energy. That corresponds with how much do we have to heat something to make it into a liquid versus how much we have to heat it to make it into a gas.
Not as much.
Not as much. Liquids have less energy than gases. Alright? Did I skip that one? Did I just not even put it on there? At least I talked about it. So. Alright, but we said two factors, right? Motion of the particles, but what else do we have to consider? What two factors? Nick, go ahead. The attraction, right? So, attractive forces between particles is strong enough to affect the motion of other particles to a certain degree. The particles in a liquid will hold on to each other, will attract each other a little bit more than the particles of a gas. What does that mean? Well, how far apart are those liquid molecules versus the gas molecules? Closer or farther? They're going to be closer, right? Can the particles of a liquid move as much as the particles of a gas? Not as much, because the other particles are affecting them, right? Particles can still move, but not as quickly, right? Mixing occurs more slowly. Things just don't move quite as fast. And because of that, right, because of the closeness of the particles, more attraction that they have for each other, right, the fact that they don't move quite as quickly, that leads us to those two properties of liquids that we've known since 5th grade, right? But now, once again, we're not just saying that they have no definite shape and they have no definite shape but a definite volume. Now we're explaining it, right? The attraction of those particles, the slower movement of the particles allows them to move freely, a little bit more freely, right? But not anywhere they want to go. Continuing with our analogy. What part of school might represent a liquid? What part of your school day might represent particles in a liquid phase? Nick?
Like
Walking through the hallways in between class, definitely, right? First, can you move? Yeah, not as fast as you can on recess, but you can move. Is your motion affected by other people's motion? Sometimes, right? You can't just go wherever you want to go. Sometimes there's people in the way. Sometimes you have to move around stuff, right? Sometimes you have to move around giant backpacks, right? Things like that. Mixing. If there's already a class out in the hallway and you get let out into the hallway, can you just go like you could on recess? Not exactly, right? There's things in the way. Things don't move quite as fast. And so all those factors of liquids, right, that would be like movement through the hallway. Good there? Next. Solids, right? What are the two properties of solids that we have to explain with our kinetic theory? What are the two properties of solids that you learned back in 5th grade? Right? Go ahead, Mark. You did the other two. So.
Definite shape and definite volume.
Definite shape and definite volume. All right? Seeing as how we've gone through the process here, I'm hoping that you can maybe start filling some things in this chart already, right? How fast do particles in a solid move? Not very much, right? It doesn't mean that they're stationary. Okay? Particles in a solid are not stationary. That desk that you're writing on right now, even though it has a definite shape and a definite volume, the particles that make it up, the molecules of the compounds that are in it, right, are not stationary. They vibrate, they twist, they turn a little bit. Not enough to affect the integrity of the desk, but there is still motion. Least amount of energy of all states of matter. If we measured the temperature of a solid compared to a liquid or a gas, what would we probably find about the temperature of that solid compared to the other two?
Maybe the lowest.
It's going to be lowest, right? Now, not always, right? Not all solids have a lower temperature than all liquids or all gases, right? But if you compare the same substance in a solid phase, a liquid phase, and a gas phase, probably going to see the lowest temperature in the solid. Right? So, less motion, right? The other factor that we have to consider is what? What's the other factor that explains our theory? Attraction. How much attraction in solids? A lot of attraction usually, all right? Particles of a solid are attracted to each other very strongly. They move much less than liquids or gases. If you think back a couple of units ago, we said that there was one kind of compound that generally exists in the solid state. Remember what kind of compounds are generally solids? Nick? Ionic compounds. Nick, why are ionic compounds generally solids?
They have strong attraction.
They have strong attraction for one another, right? They have a positive side, a negative side, and they attract each other. But we said they also attract other compounds that are ionically bonded, right? It's not just one cation and one anion that attract each other, right? One cation attracts a bunch of anions, and that gives them that nice three-dimensional shape that we call a what? A crystal, right? Or a crystal lattice. That's generally a solid because of the strong attraction. And then because of that, right, definite shape and definite volume. So, to finish off our analogy, right, what part of school represents solid phase?
Classes.
Right, here you guys are, right? Nice definite shape, nice definite volume. Are you motionless? No, right? You move in your chair, you write stuff, you turn and talk to your partner, right? Check your phone, whatever it might be, okay? But you are in a fixed location, right? You have that vibratory motion, right? Go there. To finish off that analogy, right? The other two states of matter that we discussed. Bose-Einstein condensate we kind of talked about a little bit earlier in the week, right? We said Bose-Einstein condensate would kind of be like you guys having to go through school while all holding hands, right? Not in a line, in a circle. Yeah, that'd be cool. Like, try to get your backpack on, that'd be great. So,
If there's a line, we could like always pass it down.
whoa, that would be like when you have the game at summer
Yeah.
camp, you have to pass the hula hoop like around the circle without, yeah. So.
That'd be nice.
And then on the other end of the spectrum, right, plasma. Plasma would not be pretty in the school setting, right? We said that what happens in the plasma state? Do you remember what happens in the plasma state? Nick.
Aren't the particles moving really, really fast?
So fast that atoms don't exist anymore. That protons and electrons are moving so quickly from one another, moving so fast that they can't attract each other. It's just a bunch of scattered pieces of an atom.
So it's like if there's a fire, the school everyone runs.
Well, no. That would be like the gas phase. Because each of you is a particle and you're doing your own thing, right? Plasma state would be like your arm goes that way and your leg goes that way. That's not pretty. So let's stay away from the plasma state, at least from our school analogy. So, all right, questions about your kinetic theory. We will use kinetic theory over the next couple of days to explain why states of matter exist, how states of matter change from one state to another. All right. Oh, real quick. Calendar. Tonight, in addition to finishing up your quiz, there is some reading there from the book, a couple of pages that explains kinetic theory, stuff we talked about today, and then a couple of problems about kinetic theory. Just make sure that we understand what we're doing there. Questions? All right.